Skot. Hey, Skot, welcome. Lovely having you on, mate. I don't know if you know this, but yeah, I don't know if you know this, but for a while, I've been watching your work and monitoring it, and I've actually,
What?
I haven't built it just yet, but it's
No
coming.
way. You might be the first person I've ever seen to make a board. This is incredible.
Really? No, I've got five of them just now. And I want to. I still have to order the components, but some of them, some of those components on the board are like unobtainium. The TPS stuff, fuck me, Jesus.
This is like the bane of my existence, right?
Yeah.
Like this part shortage is gnarly. Like I do this for my day job too, and I'll be designing a board and the parts go out of stock while I'm designing the board. It's rough.
What do you do about that,
It's like
man?
as soon as you find a part and you're like, I think I want to use this, you should
Yeah.
just order a reel because like that's the last chance you're gonna get.
Yeah. Man. Okay, I want to go into the background there. We just had a little bit of a conversation which we didn't get recorded, and I want to capture that because, dude, this is great. What's up with the background?
So it's a max headroom background. It's a recreation of a max headroom
Brilliant,
background.
brilliant,
Um,
brilliant.
and I spend a lot of time on Skype these days, so you got to have a cool one, or on Zoom or whatever.
Now, some people might not know about Max Headroom. Maybe you want to go into that.
Well, Max Headroom was a TV show from the early 80s or mid 80s, I guess. And the concept was it was like a talk show, and the host of the talk show was computer generated, right? And this was in the 80s, so he definitely was not really computer generated. It was a guy wearing a very weird mask to make him look like he was computer generated. And they had
Yeah, and
these
he had like a
backgrounds.
stutter, like a little bit of a movement,
Yeah.
like
Yeah, like every now and then he would kind of like buffer or something, right? And be like, this is max headroom.
yeah, yeah,
And the background was like this, but it would be kind of like just sort of like
yeah,
moving around.
yeah, yeah, yeah.
And I remember watching it as a kid and being like, this is unwatchable. Like it was so weird. And yeah, just I think it's also maybe he's British, so I didn't get the humor or something. I
Yeah,
don't know. But
yeah.
in retrospect, like it's a cool idea and makes for a cool background because we're, talking on.
Yeah, 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 exactly. A couple of talking heads as we speak.
Yes. Yes, exactly.
So, I've got quite a few questions that I'd like to go into this, into your work. I suppose probably a good entry point is how did you sort of come about with this? How did you sort of like, well, what is Bitaxe, for example? Let's start with that.
So Bitaxe is perhaps one of the first open source ASIC Bitcoin miners. So it uses a chip that's out of the Bitmain Antminer S17, which has like hundreds of them inside, and this just has one. But that's, in my opinion, it's kind of an impressive feat because this chip is completely undocumented by Bitmain, right? So
It's all documented by you, though.
yes, so myself and definitely like on the backs of others and with some help from some other people on the internet, we've mostly reverse engineered this thing, from the mechanical footprint, electrical specifications, all the way down to the register map and how we interface with this thing.
That's quite a feat in itself.
Yeah, it's
Kind
pretty
of
cool. I've
annoying.
been working on it for a while. I've been working on it for a long time, to be honest. Um, So yes, it's a Bitcoin miner, and it's the goal is to be open source, so other people are free to like take the plans and hack on it, do whatever they want, order up some PCBs, and that part of it is awesome. Like people have been kind of just coming out of the woodwork everywhere, and like, and some people have made some derivative designs, which is fantastic. So,
Oh yeah, such as.
we've got like a small Discord going where
I'd like to join that.
yeah, absolutely. I'll send you an invite. I don't know how people even find this, but people keep showing up, and I've had there's one guy on there who's taken, and I think he's put 16 chips all on one board to make not as powerful as this S17, but certainly more powerful. He's got a design going, and it's working. It's pretty cool. It's working, and so he's doing that. There's another guy who's making a PCIe card with some ASICs on it, which is kind of an interesting idea. You could put these.
Oh, so that just slots into your tower, and then you can start mining with that. Just away you go.
Yeah, like a graphics card or something, right?
Right, right.
Kind of a cool idea. And there's another guy who has just made a little handheld miner that has a little screen on it and a tiny little fan, and you could just.
Is that the nerd miner?
Yes. Okay. Yeah. Yes. Yeah. He made it first just CPU mining. So it was just mining on the ESP32 processor that he has in there. And so it was doing like, 10 kilohashes per second, right? Just like pure lottery stuff. But he's been helping out a lot, and I sent him one of my boards to screw around with it. And he's going to try incorporating an actual mining ASIC into his nerd miner so that he can increase his hash rate by like several orders of magnitude, right? We're seeing on the order of like 400 gigahashes per second. So that should be a big improvement.
It's surprising how much you can sort of squeeze out of that single ASIC. Eh? It's crazy.
It is, right? It's really, really cool. Like those chips are well done, and this has got to be like the 6th or maybe more like generation of bit ASICs, right? So they've come a long way too.
Yeah. Well, there's something that's really sort of interests me, the angle of this. A few months ago, I was sort of lying down in bed thinking, gosh, Stewart, like all these miners that are being built at the moment, they're not really considering the energy source. So, for example, you get a bunch of guys, they create these ASICs, they create these just massive boxes, which is purely designed for one thing, which is to dump as much energy into this box and convert it into as much hashing as possible. And you've got all this heat that you need to dissipate. And just as a natural side effect of that configuration, there are only a few places in the world that can actually work with this, and one of those is like Iceland, where it's like cold on the outside and you've got geothermal energy, cheap geothermal energy you can dump into this. And then when I took a step back and I thought, okay, say an engineer looks at this situation and says, okay, look at all the different sorts of energies around energy sources around us. How would I design an energy, a miner for geothermal or hydro or tidal or wind or solar? And I thought, you know what? Solar is actually a pretty good idea. Let me start designing a board. I like this. I'm going to do it. And then I went online and I saw your work. I'm like, God damn it.
Well, join in, man.
Somebody's already done this. But what's the angle? So I think there's still a long way that needs to go before it becomes solar. I mean, this is primarily going to be extract energy from the solar source. Now, why is that a good idea? Why is that interesting from a mining perspective?
Yeah, so this kind of, I think I maybe had the same thought process as you when I was thinking about this, as I was like, I want to run these things on solar panels. One of the things I was thinking is solar cells, right? The individual pieces that make up a greater solar panel are fundamentally low voltage DC devices. And it turns out that mining ASICs are also fundamentally low voltage DC devices.
Yep.
Right. So there's been some people screwing around with mining on solar, right? But the first thing they do is they have these big panels that they're connecting all in series, so they get like 70 volts, right? And they put that into an inverter and generate 220 volts AC, only to go to like that brick power supply, which steps it right back down to 12 volts, and then it steps it down to 1.5 volts on the board, right? So it's that all that changing, super inefficient. So
lots of wastage.
Yeah, right. It's a big waste. It's a lot of stuff you got to buy that just you don't really need. It isn't doing you any favors. So I was thinking, what I want to do is just have a miner I can attach to like one small solar panel, and then I can just put them on my roof, or in my yard or whatever, right? I can just sort of Johnny Appleseed, just lay these all out and over the land. So, for that, we also need wireless data communication. So, I actually looked into a couple other like wireless protocols, but I kind of landed on Wi-Fi just because it's, the easiest way to go.
Yeah. So I'm finding myself having to just suppress myself from like, shut up, Stewart, let him speak, because like all of the thought processes, all of the design decisions that you've made, I've gone through, and I'm like busy thinking, oh Jesus, yes, exactly. The wastage of energy, that the inefficiencies that happen from that conversion is just so brain dead. There's no need. You just take this thing, bolt it on directly onto the back of the board, and you can have your lines that sort of come out from it, and that can go into the inverter. And this thing, if it's smart enough, it can detect if there's load. If there's load, it won't mine. If there isn't any load, it just mines. It's a very, very simple thing,
Yeah. It was Block, I think, put together that paper. This was a couple of years ago now, which sort of, really got me stoked, right? And they kind of put forth this idea that, what you want on your house is a box that makes the decision at any given time. Say you got a bunch of solar panels on your roof.
Yes.
It makes a decision at any given time. Do I sell that power back to the grid? Do I charge my batteries or my electric car or whatever? Or do I mine Bitcoin? Because at any given time of the day, there's a right answer to that, So I thought that was really cool. And I've talked with people who were like, we need to make this box, and been very interested in doing that. But it's a huge process because there's just no open source stuff surrounding it, which is a huge tangent I could go off on. But
but we should definitely go into that, and we've definitely got the time to do that. So in places like South Africa, because I was born and raised in South Africa, where there's just the largest cartel in South Africa is the energy grid. It's Eskom. It's just a massive cartel. And what do you think you're going to sell? Do you think they're going to give you money when you dump energy into their grid? No, of course not. So South Africans, they're suffering from the issue of having their money debased. Number one, we know that as Bitcoiners. And also number two is like they can't sell the energy back into the grid. And the third thing is that the Eskom is like cutting, they're doing load shedding, basically. They're cutting the electricity to their users for up to 10 hours a day.
And I'm going to guess they don't pay you back for that.
Oh, of course not. No. But why? Because they say to the populace, look, we need to increase the energy rates. And if we don't increase the energy rates, this is not written down, this is not spoken about, we're going to cut your energy more. So you better bloody well pay us. Otherwise, we're going to cut you some more. So what's happened is South Africans just give the middle finger like, fuck you, Eskom. We're going to go off grid. and that's basically what's happening. So you can go down to Cape Town, you can go to South Africa, and you can it's just solar panels everywhere.
Really? And not grid connected.
Yeah. So many of them are still retaining the grid connection because they're under the fallacy, the illusion that eventually they will be able to sell the excess energy after you've recharged the battery. that all of that stuff is just wasted electricity, and in South Africa we got a lot of sun, so that's just a lot of wasted energy. And I'm just looking around thinking, fucking mine.
Right? Oh man, there's a lot of people on the internet talking about it, but this sort of stranded energy thing is huge.
It's insane. It's insane.
I think you just pick one of these alternative energy sources, and the amount of sort of unused stranded energy is enough to power, the whole Bitcoin network.
Truly. But you have to sort of switch your mindset away from that, take all the energy and dump it into a single box and then deal with the cooling. And you got to think, okay, no, I'm going to design this thing specifically for this energy source, tidal, solar, whatever. And then when you do that, it takes first principle engineering, which is, you're experiencing the difficulty of that right now. It's a lot of hard work, from 0 to 1, right?
Yeah, right. I mean, each of those sources has some technicalities, some way, some like load profile that you need to follow in order to properly extract the maximum amount of power from it, right? It's pretty famous with maximum power point tracking, but like all of those are going to have their special use cases, right? But we got firmware, we can do it, no problem.
Yeah. So let's get into more of the technicalities, and that's one thing I really like about sort of setting up my own little podcast, is that fuck it, I could we can get as technical as we want. What is MPPT, the maximum power point tracking? Yeah,
so it basically is an algorithm to extract the maximum amount of power from a solar panel. If you have an ideal power source, not a solar panel, like just a power supply, if you have an ideal power supply, no matter what current or voltage you pull out of it, you'll be able to get the same amount of power, right? But solar panels are not ideal power supplies. They have a limit to how much current you can pull out of it, and they have a limit to how much sort of voltage that you can pull that current at. And the tricky thing is that curve, that IV curve, they call it, is constantly changing depending on the amount of light that's hitting the solar panel. And other things like temperature, and it's just constantly changing. So in order to extract the maximum amount of power out of a solar panel, you have to use an MPPT, maximum power point tracking algorithm, to do that. And there's actually a few different algorithms that kind of you can pick depending on your use case. But like a standard one is called perturb and observe. So you just
poke it and watch what happens.
Yeah, exactly. Every now and then you just kind of like bump up the current and you see if you're getting more power out of it, or if not, you take it down, right? You're trying to find those maximums in your curve.
Sounds a bit like transmission control in these networking protocols. You want to I don't know, let me just explore, and then you start bumping it up. Oh shit, take it back down. Yeah,
there you go. Yeah,
okay,
yeah, totally. That's what it is, right? It's because they're sort of like fickle little devices, and you could, if you wanted to be dumb about it, you could just sort of have your max power that you're trying to extract from a solar panel be really low, and just hope that you never with a crash the solar panel. But who wants to do that, right? We want to be as efficient as possible and get the maximum amount of power out of a solar panel, which is already like horribly inefficient.
Do you see, for example, the design that you have at the moment? You've only got a single ASIC on here. Now, there are different sizes to these panels. They start off at I think 50 watts, and then they move all the way up to 500 watts, which are this great big lugging device. Do you think it's possible to have multiple ASICs, or you have different boards which are suitable for different sized solar panels? And if so, would you have different amount of ASICs on there? The logic would be significant.
Yeah, that's a great idea. I think once we've got a handle on how this ASIC works, which we're getting close, but wait, right? There's a lot of different options here as to how this can work. And I actually do think that there'd be more than one ASIC on a board. And one of my previous designs, I put 3 ASICs on the
I
board.
saw.
And I was like, this shit's
Fuck
not
that.
working
Abort.
at all. I gotta go back to one and really wrap my head around this. So I said the same thing to that guy that was making 16 on the board, because he was messaging me like, it's not working. I'm like, dude, yeah, these are pretty complicated things, and we have no documentation. So keep it simple, at least in the beginning. But yes, you're absolutely right. Like, there could be different configurations for different size panels for different applications. You can get solar panels down to like less than 1 watt, and you can get them made up to huge ones if you want. There's actually a company, I'm blanking on the name, I'll have to look that up, but they will make custom panels for you.
Oh, right.
It's not all that expensive, right? They'll take the solar cells and they'll put them in whatever series parallel configuration you want.
Fascinating.
And they encased and waterproof. And
oh, okay. Oh, I suppose also there's all the, when you start going down the solar panel rabbit hole, there's so many different variables that you got to play with. Like, for example, I think the optimum temperature for a solar panel is, I think, was it 25 degrees Celsius, and then as soon as it starts going higher than that, it just gets less and less efficient. And then you start thinking, okay, well, now I need to start cooling this panel somehow, and then, oh my god.
Right, and we got to cool this ASIC too, right? Because like, once you get it built up, this is going to look weird with my green screen.
Oh god, yeah. Look at that.
Green board on the green screen doesn't work very well. But yeah, once you get the fan, the heat sink on there, and the fan on there, you're running it at 400 gigahashes per second, right? You have to have a fan on there. You have to have a heat sink on there. There's no choice. It will just burn up. So these are all difficult things to deal with when you think about, I need to send a waterproof enclosure on the underside of a solar panel. But I was talking with some mechanical engineer people about that, and I think there's some options.
Okay. Yeah. What are those options? Because I have to write down stuff. What are those options?
Well, okay. So I this is not my area of expertise, but what about ground loop cooling, like geothermal cooling? Because underneath the ground, not too far, is a very consistent temperature. I think it's like 55 Fahrenheit, right? So, your solar panel is stuck on a post that's in the ground. What if that post,
fucking great idea,
is your heat pipe, right? I think maybe some of your viewers will know that I'm
explain what a heat pipe is. Explain what a heat pipe. That's critical. Explain what a heat pipe is, because that's critical for this.
Oh man, I don't know what a heat pipe is. It's like a pipe.
Okay, I'll explain what a heat pipe is. Okay. So a heat pipe is normally what happens is it's a copper thing. You can see these things inside computers. What they do is they communicate. They transfer heat from the hot area to somewhere else. And what they do is it's quite an amazing piece of technology. On the inside of the heat pipe, it's very, very porous, and the copper is very, very gnarly on the inside. And I think they evacuate the temperature in there, but insert just a wee little bit of water inside there. So there's actually some moisture in there, but in gaseous form. Now, what happens now is that on one end of the heat pipe, that heat then gets absorbed by the water moisture, and it gets communicated to the other side via this gaseous transfer. And basically, you can if you hold a heat pipe in your hand, just with the body heat, you can cut through ice. It's truly amazing to see this technology. The heat is transferred from your hand directly into the ice. And if you look at like thermal cameras, it's insane how quickly this is. It's absolutely insane how fast the heat transfers.
This is awesome.
Yes.
This is exactly what we need. Like,
And Yeah, you can get heat pipes made on Taobao for cheap.
All right. Well, that's your neck of the world. So
Yes, it is. But I think I think the heat pipe idea is a really excellent idea. So actually, the heat pipe wouldn't be the entire thing. You would have to run the heat pipe from the device all the way down the length of the thing and maybe into the ground. But I wonder that's those heat pipes are pretty long then.
yeah, it's going to be pretty long, right? And I think the thermal conductivity of the ground is really low, which is why it stays that constant temperature. So you might have a problem like actually conducting the heat away from this thing once it gets in the ground. But I do know that like, you can do geothermal cooling in like houses and buildings and stuff, right? It's a thing.
I don't know about that. Yeah. No, I don't know about that. But okay, so but you see that's when you start to move away from the whole yeah, just dealing with a PCB now, and you start moving into the whole fucking rig, you know, the whole stand, and then then you have to set up a company to do like, you know, setting up of these devices, and then oh gosh, the complexity starts to enter the picture quite a
Yeah.
lot at that point.
Yeah. Well, we can dream.
Yeah, oh yeah, sure. Engineers will design.
Well, this is one of the big motivations for open sourcing it, right? Is like there's way more here than I can do,
Yeah,
right? And if we can put the tools out there so that someone else who wants to screw with this doesn't have to start from ground zero and can
yeah,
just grab the design and run with it, right? This is why
yeah,
this is how the internet is here, right?
yeah,
Like,
yeah.
right? Like, you know, what's his name made the Linux kernel, and now look where we are.
Yeah. Would you mind going into the actual circuitry of this? Can we do
Yeah,
that? Okay.
yeah.
So I've got everything ready to go, or we can choose to use your screen and you can navigate the circuitry and how everything comes together. Let me just
Sure. Why not? I
okay.
can maybe share my screen. That way I can point at it. That might
Okay.
help.
Okay. Well, all participants can share. Who
All
can share? All
right.
participants. Okay. So you have the permission. You have the privilege to share now.
All right. Let's give this a try here. Share screen. That one.
There we
All
go.
right. You
All
got it?
right.
Okay.
Yes, exciting.
All right.
Bitaxe, yo.
Bitaxe, yo. You know, you got to type something in that field. I don't
All
know. This is like
right.
the problem with engineers is like naming things.
Yeah. Okay.
All right. So first this is KiCad, right? And so KiCad is a fantastic open source free ECAD program. So for laying out circuit boards, right? So everyone needs to use it. Everyone needs to check it out because it's so awesome. I've been doing this professionally for a long time, and I've used lots of very expensive software packages, and KiCad or KiCad, depending on what camp you're in. It's fantastic. It's so good. Like I'm so much more willing to deal with stupid issues when I'm not paying $4,000 a year to use it.
Jesus, as much as that.
And they're
I've
not even, that's Altium, and it's just not even that good.
I,
So,
I've only ever used KiCad, so I have no idea about the other stuff.
oh, okay, wow. And if you've, yeah, KiCad was pretty rough around the edges until maybe 2 years ago, and they just like exponentially increased it. It's
I,
fantastic now.
I see
I
you
use it
using
professionally.
I see you using number 7 now, the latest version now, right?
Yes,
Okay.
I love it. I actually convinced my company to be a sponsor of KiCad, and
Oh, you did you?
we
Ah, well
donated
done.
about what we pay for one Altium license. So,
Okay,
uh,
good.
all
Okay.
right, rant over. Um,
Plug over.
yeah. Okay. So, we have 4 main blocks. This one, can you see my cursor? Like, does it
I
kind
can
of
see
come?
everything.
Okay, cool. So this one here is the power block, right? That deals with the input voltage, which in this case is 5 volts, just a nice, good round number. And it outputs It outputs 3.3 volts, which is for the microcontroller, the ESP32, which is over in this block. But maybe more exciting, what it does is it contains the low voltage, high current buck regulator, which takes the 5 volts and steps it down to about 1.5 volts for the ASIC.
Isn't the 5 volts an input?
5 volts is an input, exactly.
But you've got it listed as an output.
This here is the sorry, it's a little bit weird, so I didn't label it. That's the input, 5 volts. This is actually a 5 volts output that goes to another part of the system.
Okay.
And I can show you what the goal is there with that, but I should label that. There we go. How about that? Okay, so we have that 5 volts input, and yeah, that arrow's facing the wrong way.
Yeah, exactly. Yeah, double click on that. Double click on the 5V. Wait, double click on it.
Like that?
Yeah, no, the 5V, double click. Yeah.
Yeah.
Oh, I can't see the pop-up window. Oh, okay. And then you should see it, that you changed it. That's correct. Oh, that explains everything now. I can't see the pop-up window. Okay, now it looks good.
Okay. All right. Okay. I'll keep that in mind. Yeah. It doesn't really change anything.
No, it doesn't. It doesn't.
But it looks way better.
I'm being fucking OCD. I should shut the fuck up and just let you talk. Go, man, go.
No, it's all good. It's all good. Like, when I was laying this out, I was like, this isn't my day job. I'm just like nights and weekends, right? Screwing around. I'm like, I'm not going to like do all these goofy little things that like I have to do for my job. And so I kind of was like wild style in the beginning. And then some other people saw it and they're like, what does this mean? What are you doing? I'm like, I was just being lazy.
Sorry. Okay, keep going.
Okay, so this is it's a Texas Instruments controller, a switch mode buck regulator, so it steps the 5 volts down to around 1.5. This is kind of a tricky part. This is finding a part like this that can do a lot of current, like 20 amps at 1.5 volts is tough, and part shortage, it's even tougher.
It's unobtainium, man. That shit's hard to get. Fucking hell.
Yes, it is. So I think this one's still in stock. Were you having trouble getting this one too?
Oh, you think it's in stock on ti.com? Is that what you're saying?
I think it's in stock on DigiKey.
Oh, is it? Oh, because I found that if you go to ti.com, they say, oh yeah, it's all in stock. But then when you make orders, then they cancel the order, or else they'll be like, oh yeah, no, it'll be like the lead time is now 4 months or something, and it's like fuck. So okay, I didn't know if it's on DigiKey. Okay, well, last time I checked, it wasn't there. But anyway,
it'll be a lot more expensive, but I think DigiKey has it. I think someone was just going through this the other day, and they were able to order everything except for this power monitor IC.
Oh, okay. This is also unobtainium stuff, eh?
Yeah, that's a tough one. This part's optional.
Okay. All right.
So I guess while we're here, this part right here, the power monitor, is part of this plan to do maximum power point tracking on solar. So it measures the voltage, it measures the current, and calculates the power, and sends it over I2C to the processor.
Okay.
So that we can do that perturb and observe thing.
Yeah.
So it's hard to get, but if you can get one, it's a cool part. And again, you know what? There's a lot of other ways to do this. This is a little bit of me being lazy and being like, I'm just going to throw down this part that I know and I've used before. So yeah, that a bunch of people complained about this. So I think in a future rev, I'll replace that with something a little bit easier to get, maybe a little bit harder to design for, but what the heck.
So, okay, I think now's a good time to sort of enter this question. A good mate of mine, he's very good at electronics. And I asked him to take a look at the circuit, and he was like, he was saying that, you know, using this sort of, okay, I will try to repeat what he says. If you ask me questions, it's highly unlikely I will be able to expand on what he says. And he's one of those sort of people that just says like a few words and you have to, like, you know, read books to understand what he's talking about. And electronics is not my background. I'm more software. So I will try to go into this, and hopefully you'll be able to understand and fill it all in. But he was like, he says, ask Skot about what is the phase margin of this thing. I don't even know what phase margin is. I don't know. I don't know this.
I don't know. I think that's a property of the switch mode regulator. I think it has to do with the switching frequency of these transistors here.
Okay.
But I couldn't tell you off the top of my head. I also probably couldn't explain what phase margin is off the top of my head. But I know it's a property of a switch mode regulator. Well, okay. I think it's a property of a switch mode regulator. Okay. So
because he was yeah, keep going. Yeah.
Well, I'm curious. Why did he want to know?
Well, okay. So he suggested that if you don't know or understand what the phase margin is, for this kind of device, when it is exposed to different sort of temperature gradients and whatnot, it could just go off. The power just go off, and you have no fucking knowledge why it did that, and it becomes almost impossible to reproduce these issues. So again, it's like I'm talking, I have no idea what phase margin is and how it works, and I don't understand this stuff. But he did say this. He said you can probably solve now. Let me if you could stop sharing, and then I will take you to something, and then I will share. I will share the desktop like this, and then I will share that. And then you should see something at the moment. Is that right?
Yeah, I'm gonna ask.
Shoot. Okay, so he said something like these polar modules might be able to solve your issue. So
whoa, I like this.
Yeah.
0.8, that last second paragraph at the end there, it says provides up to 60 amps at 0.8 to 3.6 volts. That is something that I
so he was saying this polar module should be able to solve your thing. He's like the phase margin of this sort of thing is well fuck, I'm speaking as if I know. Like the phase is well calculated. I don't know. I don't even know how to describe.
I'm writing this down. This is cool.
Okay.
So, you know, this to me looks like it might be related, but I've had this thought lately of like, a lot of semiconductors have a really low voltage. They operate at a really low voltage, right? Like less than 2 volts is very common, right? And all these, like, hot shit graphics cards that are hundreds of watts, they've got this solved too, right? Like they know how to do low voltage, high current. And I think that might be sort of, this POLA or point of load alliance, or this industry might be where this comes from, which is definitely something I want to look into.
So yeah, apparently he was my mate Sebastian. Actually, maybe you might know this, Sebastian Boroduk. He's the guy who created Milky Mist, and all of the FPGA miners after the ASIC generation are based on the Milky Mist, all of them.
Okay.
So basically, and Sebastian fucking hates Bitcoin. He thinks it's like wasting energy, and I keep having these drunken beer conversations with him. I'm like, dude, you have made such a contribution to humanity through the Bitcoin mining and your FPGA stuff. And he's like, oh God, I hope not. I'm like, dude, you need to understand this shit, you dumbass. But I mean, but he's great. He really understands the electronics, and he's the one who came up with this polar idea. And he was like, yeah, you need to watch out for the let me unshare. I'll stop sharing, and then you take over again.
Yeah.
And yeah, so all of the we can all be thankful to Sebastian from the mining perspective, because yeah, his work is what people used as and it's all open source, the Milky Mist, to start the increasing the hash rate, and that caused the race to happen for people to start going into ASICs and all of that sort of stuff. So yeah, okay.
I did a little bit of FPGA mining back in the day.
Oh, you did you, eh?
2013,
Yeah.
maybe 12, 13, 14, something like that, right? Like the first ASIC miner, the Butterfly Labs one was just kind of going into like, maybe
I
they
bought
won't
that.
get there. You bought it. Did you ever get it?
Yeah, I got it. But those fuckers, they shipped it so late. It was just so, everyone was pissed off. You're like, you fuckers are busy mining with my ASIC miner that I bought. Bastards.
Yeah, I feel like this was right around the time that like some drama was starting to happen with these
That's
guys, right? Like everyone on Bitcoin Talk was talking about pre-orders, and a lot of people were like, wait, this isn't showing up. But I was working in a university lab, and we had it was actually, they had a lab there for the undergraduate students doing digital design, and they had badass FPGAs like on every lab bench.
Oh, lucky.
And and they, when they weren't in there, no one was using these things. So I didn't write it myself. I just downloaded some open source FPGA bitstream for Bitcoin mining and loaded it up on a few of these things, and
all of these things.
We'll never tell. Started mining a little bit and screwing around with it, and it was really cool, right? And it was these designs were open source, which was was awesome, right? Like that was so cool. People could take that and they could screw with it. And I don't know, we just don't have that now, which is one of the motivations for this. But yeah. I remember it was each one was 25 mega hashes per second, which was better than CPU.
Yeah,
and maybe better than a GPU, maybe.
Yeah,
but yeah. So the solution was just get a bunch.
Yeah, no, I was on CPU, then GPU, and then I skipped the FPGA stuff, and then I went to ASIC, and then I was like, God damn it, electricity is too expensive. It's just easier to buy Bitcoin.
It really is. It really is. But so CPU mining, I never did GPU mining, but I assume that the software was available open source, right? For GPU.
Yeah.
Right. So, and people were just hacking on this. And it was like, it wasn't until the ASICs came around that really things got locked down and people got real stingy about these designs.
Yeah. But I mean, it's also understandable, because you try making ASIC, you need millions of dollars to create the what's the masks that go into the masks that go into these chips.
Tape out the masks.
Exactly. I've just been studying a little bit about how that stuff works. And if you make one mistake, bro, that's it. Your chip doesn't work. You're done. It's like goodbye those millions of dollars to do that round. So that's why I think everyone became stingy. But the thing is that there's
if you're in the business of selling chips, right? You've made this mask. Now you can crank out these chips for very little money, right? So selling the chips is how you make your money back for that mask. Why wouldn't you want to sell them to as many people as possible?
I think that'll happen. Somebody will do this. I think that's going to happen at some point. But how many companies are actually making these FPG? I mean, these ASICs at the moment? There's probably like 3.
I was going to say maybe 6.
6? Okay.
Right? Intel's getting into it, supposedly. Yeah. Bitmain, the company that makes the InnoSilicon, that make the What's miners.
Yeah.
Bitfury.
Yeah.
How many do we have now? And there's a couple other weird ones.
I think they can just turn more of a profit if they sell the entire device. Do you see what I mean? They would do more value add on. Eventually, somebody like Intel's going to be like, fuck it, we're just gonna sell the chips, and then everybody else is going to be like, well, okay, we'll do that too. And then when that happens, we're going to have the documents and the PCBs, and just like plug it straight in there and make it work.
I think it'll happen, right? We're just early.
I think we're early. Yeah, I think we're early. And then freaking toasters are gonna have like ASIC miners in there.
Yeah, right.
Okay, let's keep going with this circuit,
yeah, okay.
man.
All right. Excuse me. Okay, so this whole block up here is the that is the buck regulator that steps down the voltage. And one of the cool things about this, and I think one of the things that's going to make this miner more configurable and perhaps more efficient than any other miner that uses this same chip, is that this regulator's output is configurable by software. So you can adjust the voltage using this. This is just a current, they call it current DAC. It just supplies some current sources or sinks some current to the feedback pin on this regulator so that you can, essentially under I2C control, you can change the output of this voltage regulator up here. So that's pretty cool. You can change it. You can go all the way up to, I think it's like 2 volts and all the way down to like 0.5 volt.
Okay, so in combination with this power monitor, and you got your MPPT algo running on the chip, you can actually adjust it as needed.
Yes.
Is that that's the goal, right?
Yeah. So there's I should say it here because I think some people are going to catch on to this if they haven't already, but this is like establishing that first date for the patent lawsuit or whatever, but I'm going to call it maximum hash point tracking. So it's like maximum power point tracking, but we don't care necessarily about maximum power. We care about maximum hashing. So maximum hash point tracking. And there's a couple different variables that we have to tweak in order to sort of change the load on the solar panel. One of them is the hash frequency that the chip runs at, and the other one is the core voltage, what this voltage regulator outputs. And when you change those things, you can change how much current the ASIC draws. And so you can use that with like a MPPT like algorithm to get in that sweet spot for the power source that you're connected to.
Okay, great. Okay, so all right. So
basically this allows you to tune the power that this whole circuit draws to extract the maximum amount of power from your source.
No, extract the maximum amount of hashing from your source.
Yes, there you go.
Yeah.
Yes.
And it's interesting. I actually don't want to even open up that chapter at the moment. I'm still grokking it at the moment. Okay, so what you're doing now is you're declaring prior art.
Yes.
You're stamping it right now. It's like, okay, great. This is what we're doing in the podcast.
And just so everyone knows, we're open sourcing this, right?
Oh, good, man.
The company that we're forming to keep this proprietary.
Oh, hang about. So you're actually going to register the patent, but it's going to be a defensive patent. Is that right?
I'm not going to register any patents. I hate that crap.
Good man. So this is just sort of putting it into the public domain, as you say.
Yeah, right. Like when you go to get a patent, don't you have to like do a search to see if it's existing or not?
Dude, you got to do all of that sort of stuff. I mean, trademarks are okay, but patent is it's a nightmare. I mean, maybe if you're large enough, you can do it as a defensive sort of thing. But I don't know. I think this is just it's a waste of time.
Someone's going to patent it, right? They're going to pay a bunch of money to patent it, right? And then someone's going to go and infringe on it.
Yeah.
And then their lawyers are going to find this podcast right here. They're going to be like, that original patent is thrown out because it was already a thing.
Yeah. Okay. I like it. It's okay. I will speak about it. It's almost like, okay, so hashing is the ability to project power, joules of energy into cyberspace, right? This is the whole Jason Lowery thesis, which is actually a very old thesis. We've known about this for a long time. He just sort of packaged it into a nice sort of a form.
I need to read this.
Sorry?
I need to read his book.
In the
Yeah.
form of a thesis,
Yeah.
which I've just purchased. And yeah, it's kind of interesting. So it's almost like hashing. Because the more efficient your system gets, the more hashing you can do at a cheaper, at a lower cost. So hashing is almost like it's almost like voltage, can I say? It's almost like the ability to project more efficiently joules of energy into cyberspace. Do you see what I mean? It's like it could be like this, you might have the same amount of joules of energy derived from your system, but if your system is more efficient, it can project the joules of energy further or deeper, or I don't know, like better into cyberspace. Do you know what I mean?
Yeah, right. I think there's probably a mechanical analogy here for this.
I'll
I was
let
trying to
you
think.
I'll let you come up with that.
Yeah, I'll let you know when I do. But yes, right. Like I think there was some drama like this week because Taylor was getting this wrong, but like they're yeah, yeah, right. What does it mean when you get more hashes for a given amount of energy?
Oh, that tweet, yeah. And then people were like complaining about that tweet.
Yeah.
Yeah, to me, it's like you can more efficiently project joules of energy into cyberspace better. So yeah, I don't know, like I don't know what it is. Voltage,
But
what is it?
on the other
It's
hand,
a whole new thing. Hashing is a whole new thing.
on the other hand,
Yeah.
right, there's always the difficulty adjustments, right? The network is constantly adjusting so that we need, to basically adjust for how much ever hash is out there, right? So it's for some reason only every like 2 weeks or whatever, but like it is continually adjusting to absorb sort of whatever efficiency gains we have
Yeah.
in hardware.
That's a good point. Yeah. Yeah. I don't know. Hey, we're still figuring this thing out. We're still
So
figuring
like
this thing out.
Bitcoin mining is a direct conversion of energy to money, right? Like
Yes.
probably the most direct conversion. And I think the difficulty adjustments of the Bitcoin network are to keep that exchange rate the same.
I agree with you. And specifically the solar energy is just truly amazing. It's just like you wake up in the morning, it's like, oh, it's a sunny day. Great. I'm making money.
Yes, I really look forward to having, some dashboard or maybe an app on my phone that I can look at and be like, oh man, it's what a sunny day. Look at how much I'm hashing.
I'm feeling extra happy today. I got the vitamin D and I got the money.
Sun is shining, the weather is sweet.
Yeah. Okay. Back to the technical stuff then, man. Okay, so what we got here is you got maximum hash tracking.
Point tracking. Yeah.
That's brilliant. That's really good.
Yeah. So yeah, this is the power subsection of the circuit, and I was trying to think about this maximum hash point tracking
as you were doing that, but I don't know if you could do the same thing with those polar modules. Hey,
I don't know. We'll have to look. Maybe they are adjustable. It gave a range on the output, so maybe.
Yeah, true. That's quite interesting. Yeah, so the phase margin, I believe, according to Sebastian, the phase margin can really stuff up your circuit, especially when you put the solar panel out there in the sunlight and different temperature gradients. So like random ass stuff could happen to it. Whereas if you use a polar module like that, all the power is contained on that little device, and all the calibrations, the spacing of the vias, the traces, also all of that sort of stuff contributes, I believe, this is how I understand it,
Oh, yes.
contributes to the phase margin of that little circuit. So you just get the output of that thing, and you don't have to worry about this circuit sort of dying because it hit 42.37 degrees Celsius and the wind was at this particular rate. You see what I mean? I don't know.
Yeah, I by no means an expert of this power supply stuff. I used a kind of neat tool to design this one called WebBench. It's a tool from TI. It
Oh,
only uses their parts, of course, but you can basically put in the specifications that you want,
all
uh,
right.
and usually the part that you want, and it designs the circuit for you.
Great.
So, and including the layout, the board layout, right? Like how to lay it out for the lowest amount of noise. I think it probably tells you the phase margin of the design. Um, I should go back and look at that. But
Actually, I think that's really important, and it makes a big difference now that I know that this circuit is designed with WebBench. It really makes a huge difference, because when I saw this and I spoke to Sebastian was like, it could be amateur hour here, it could be amateur hour, and I was like, really, are you sure? And it's difficult for us to assess this, but I know that WebBench actually does, from what I understand, I'm no expert in this stuff, but WebBench actually seems to be pretty good. So if I know that maybe a comment over here designed by WebBench, that would be pretty good.
yeah, that is a good idea.
Yeah. 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 That's that makes me much more like confident to sort of progress with this. It's great. That's great. So
Yeah, WebBench is kind of a hokey tool.
a what tool?
Uh, it's a little bit hokey. It's a little bit
Hooky.
hard to use.
Is that an
Hokey.
Americanism? What is that?
Yeah,
Like
maybe
kiss?
so. It's like
Is that's
hokey
like
pokey.
oh, hokey? Oh, I thought you said hooky. I was
Okay.
like, okay, you're going around the back door, kissing girls or something.
um,
All right.
yeah, it's a goofy tool to use, and it doesn't like sync with your design, right? So it's like it gives me a bunch of PDFs, and you have to like go and manually do it. And so then like if you want to change any parameters, you kind of got to like start over.
I see.
Uh,
I see.
but,
Okay.
yeah,
Cool.
it's definitely cool. All right, so let's go up out of this sheet, and
Wait.
right. So we were just looking at the power block,
Yeah.
and probably the next most interesting block, or the most interesting block maybe, is the ASIC block. So that's here. Um, and this has gone through like a lot of iteration, and I still don't know if I've got it totally right, but it does seem to be
Oh my
working.
gosh,
Um,
this is so interesting. I
yeah. So
I
there,
can I can see the pain and suffering that went into this. I mean, this is just like tough. Okay.
yeah.
So what are we
Bit
looking at now?
Bitmain, to their credit, has produced a series of repair manuals that contain like the world's worst looking schematics that are like totally disjointed, and it's like in a Microsoft Word document, and it's like awful resolution, but it's there. And from there, we could get the pin out and the names of the pins. So this was huge. This was huge. We couldn't have done it without this. And
Oh, you poor fuck. Oh, you poor
yeah,
fuck.
I mean, I actually first thought of this project with the first Bitmain ASIC, that like the
Oh
BM1381
yeah.
or 4, I forget which one it was.
Uh,
Um, and I bought a bunch of them and was trying to reverse engineer it from those little block eruptors that they made. Um, but didn't have the repair manuals for that, or didn't know that they existed. I don't know if they existed or not, but that was hard. That was hard. I didn't make any progress on that one.
so what was the Rosetta code, Rosetta Stone for this, the BM 1397? Was it that repair manual? The word repair manual?
There's several, right? There's the repair manual. There's the S17, which is the miner that Bitmain makes that has this chip in it, right? So
Okay.
we've dug into those. There's also the Gecko Science, what's it called? Compact F. I don't know. Have you heard of this?
No.
So there's a guy named, I assume it's a guy, person named Sidehack, and they're on the Bitcoin Talk forum, and he makes USB stick miners.
Oh, that dude. Oh, yes. Yeah.
Yeah, and so he's been doing this for a while, and he's made them with a lot of different Bitmain ASICs. I assume he's going off the repair manuals, but he doesn't say. He's pretty secretive about it.
Oh, is he? Oh, I see.
Yeah,
I see.
yeah. I tried hitting him up, and he gave me a couple little freebies, which was nice. I appreciate that.
Okay.
But it's not open source.
Okay.
He
Yeah.
sells them. They work good. They work great. It's nice. I think a lot of people are into them and use them.
Can't you
But
X-ray his circuit? Go to the dentist and get an X-ray.
yeah, yeah, and it's not even that complicated of a circuit, right? So just looking at it, you can kind of tell what he's got going on there. And
Is it a two-layer board?
it's what's that?
Two-layer board.
It's a 4-layer board, but it's just
Okay.
power on the inside.
Oh, yeah. Okay.
So yeah, looking at it, which I did very closely, you can tell that I think he's going off the repair manuals. But I don't want to like rip on him at all. Like
No.
his Gecko Science USB stick miners are fantastic. People have found blocks on them solo mining. Like it's cool, right? He really like kickstarted the alternative miner ecosystem, and yeah, he's out there doing it, and that's great. And I think it's like a full-time job despite his side hack name. But
yeah.
So anyways,
Okay, let's go into this.
You asked me what the Rosetta Stones were, and
oh yes, yeah, sorry, yeah.
Bunch of different things. We had to cobble together information from a bunch of different sources, just talking to people. Made a friend with I guess I shouldn't say too much about it, but I made a friend with a professional ASIC repairman. And he has some insights into how this works too, because he repairs them all day long. So that was great to talk to him. And anyways, this is what we've come up with here. This is the ASIC. It's in a horrible package. Like it's, like normally when you're dealing with electronics, there's standard packages, right? Like
yeah,
the one with the pins, and QFN or DFN means it doesn't have pins, it just has little pads. And this is not a standard package. It's a very weird package. Like it doesn't have pins, it has pads, but they don't extend to the outside. They're only underneath. So it's like an LGA package in a way, which is a land grid array, but it's still a DFN, but the pins don't extend to the outside. So, and it's a weird pitch. The spacing on the pins is totally non-standard. I made several boards where I had that pitch wrong, and it did not work very well.
God damn it.
Yeah. So, I should say the pitch. It's weird. It's not even like a round number, right? It's like normally 0.65 millimeters is like a standard pitch, right? But it's like 0.48 or something really goofy like that. So it was a pain in the neck, this package. I don't know why they did that. But one of the things that happens is when you solder this chip on here, there's no way to see the pins. So you don't know if you've soldered it right or not. And you can't look at it under a microscope and see. You would have to X-ray it or something. And that's just, who's got that capability?
Yeah.
So it's hard to solder. It's hard to solder. I don't know if that was like a defensive mechanism on Bitmain's part.
Probably might have been, hey? It might have been.
Yeah, maybe.
Yeah.
Maybe.
So what we've got the address are ADDR012, and then you've got these jumper. What are they jumpers? They're little soldering bits that you can
They're
sort of
jumpers.
solder.
Yes.
Yeah.
They're solder jumpers.
Why do you have them?
Solder on there. They're on there because I think I might understand now what those pins do, but certainly when I was laying this out, I did not know what those pins do. And there's a little bit of disagreement as to what they do, but I think they're a way, if you have a lot of these chips in a chain, they're a way that you can select an address for each chip so that you can individually address each chip.
Oh.
But because we don't have any data sheet, I didn't know, what is zero address or whatever. And so I wanted to
Okay.
had a guess, but just makes it so I'm not hosed if I picked wrong.
Yeah. Okay, so you'd be maybe a binary representation. You go up to 256 chips.
Well, actually, there's only 3 of them, so only 7.
Oh God, yes. Sorry. Yes. Sorry.
Yeah, right.
Yeah, I missed that completely.
2 to the 3 is
Yeah, sorry. Yeah, that's right. Yeah, you need 4 to go to 256. Yeah, sorry.
yeah.
I'm a dumbass. Okay.
No, it's kind of weird. So
Yeah.
yeah, if I had to like explain to someone right now exactly what those pins do, I wouldn't have a really good example. But I do know that when they're long chains, like on one of these hash boards from a big miner, um, those pins are either grounded or floating, and it's different for everyone in the chain.
Oh God, I see. Okay. What about BI?
um, so BI is this whole chip is set up so that all the data pins, there's inputs and outputs.
Yeah. Okay.
Everyone, you'll see like a CO and a CI.
The inputs on but there's an RO on number 10.
RO and an RI, and there's this NRSTI and NRSTO.
Oh, so they're designed to be able to compose the chips together in a grid-like of a format.
Yeah.
Is that correct?
Yep, exactly.
Okay.
Like in a chain, in a long chain, right? You can just
Yeah.
and there's another cool thing which I'll tell you in a second, but like those are all signals that you use to communicate with the chip. Like for example, CO is command output and CI is command input, and that's serial commands. And so if you send a serial command into this thing, it'll relay the same serial commands out to the next one in the chip.
Oh, so it's just relay.
Yeah. And so new in the BM1397, which is this one, is this pin mode pin right here, which is just actually really cool. Because depending on the state of pin mode, it flips which side is an input and an output.
Oh my God.
Yeah. So if you wanted to like, do a chain and then like have another one like to be in a grid, to have another one be up here, upside down, you can switch to pin mode. And now the inputs are on the other side of the chip. It just makes routing on the board better. It's wild, and they use it.
So does that mean all of the names would just flip?
They don't flip exactly. They flip sides though. They flip sides of the physical chip.
Oh, I see.
And I have it laid out here where these pins are on the side of the chip that they're on.
Okay. Oh, interesting. Okay, so now you can create a nice sort of like a snaky chain if you want to. Interesting.
Yep.
That's interesting. Is that the interest? Is that the thing that you wanted to tell me about?
Yeah.
Okay.
Yeah. That pin mode. I think that's really cool. That's
that is.
Like, yeah. Because the BM1387, which is the ASIC before this that was in the S9, didn't have that, and it just kind of made layout just annoying, right? Like
sucky.
You'd have to sort of do a bunch of vias and stuff and go around or whatever. But the layout on these is really clean, which is good because when you're laying it out, you want to have just massive power planes, because dealing with high currents, you want to have massive power planes everywhere, and you don't have a lot of room for all these pesky little signals going everywhere.
Yeah, not at all.
Yeah.
What is U1? That's it. That's it.
U1. Oh, this here. Yeah. That's the oscillator. So it's a 25 megahertz clock source for this chip. And you can see that it goes to clock in.
Yeah.
And CLKI is clock in, and look what's over here, clock out. So you only have to have one of these for a whole chain. And
great.
Okay. Clock all the way down the chain. So it's super cool like that. These are pretty cool right here. This temp P and temp N. That is a temperature diode that's on the chip itself. So you can read the internal temperature of that IC. Pretty cool. That's standard stuff for ICs. It's just like a diode that they put in there. But pretty cool. These down at the bottom here, these things here, those are the IO voltages.
Okay.
The entire chip runs at IO voltage is 1.8 volts.
Okay.
And then I think the part of the clock system, the PLL, runs at 0.8 volts.
Okay.
Whereas the core voltage could run at 1.5 volts, right? So there's just a bunch of different voltages going on there.
Why do you think?
I think that's pretty common with
Is it? I don't know. Okay.
advanced like semiconductors now.
Oh.
Like back in the day, it was all like 5 volts, right? But it turns out the switch at a transistor takes the same amount of current no matter what the voltage is. So you can use less power by just dropping the voltage like way, way down.
Oh, I see. I see. Where does the data go in? Because okay, so what this chip, I assume, will take a certain amount of data and then it'll calculate the hash.
Uh-huh.
So obviously you have to have some sort of random number on there to do the nonce. And then you send the data in.
It does the nonce, right? Nonce is a 32-bit number, and it does them all.
So you just give the payload or whatever the data is, and then
yeah, exactly. You give it a template sort of block header, and you can give it a nonce to start at so that you're not duplicating work on the whole chain. But it will just start increasing the nonce by 1 and hashing it every time. Right.
So, but then you also want to tell it the exit conditions, which is to say, oh, I want a hash with 4 zeros after it, in front of it.
Yeah.
Is that what you do?
Yeah. It has a target difficulty, and so you can send it. One of the registers is I think one of the registers is the target difficulty. So you can set, like, I don't want to hear anything from you until you hit that difficulty.
Great. So actually, it's really quite convenient. You just sort of give it.
And it's made for doing this.
Yeah, that's great. It's a little bit more complicated than I thought it was, actually. Huh? Oh.
Yeah, and I guess one of the downsides is that if it doesn't find a nonce above or below your difficulty in the entire 32-bit nonce range, it just doesn't say anything. It just goes off into la la land. So you actually have to you as the sort of miner, the firmware that's doing the mining, has to stay on top of that and make sure you send it new work before it cycles through its entire nonce range.
So it's not a very diligent, conscientious employee. This thing just like, okay, I'll work, and then it just stops working. It just shuts up. You have to keep chasing it. Beat it with a stick.
I don't know why they do that. Yeah, exactly. You got to keep an eye on it. Otherwise, you're gonna waste a little bit of power doing nonsense, and that all adds up.
Okay, interesting. Very cool. Very cool. What's TF and RF?
Those are test pins. I don't know what they do.
Okay.
I think they probably, when they're what's it called? You like, before you package them all up, you can like put probes on the die or on the wafer, test out the chips. Maybe it's something to do with that. I don't really know.
I see the NRST, the reset, just relays across the whole chain too.
Yep.
Yeah.
You asked me what BI is, and I forget.
Oh, never mind. I mean,
I think it's like there's these. It's called flow control. There's a couple flow control pins where it can say, like when you're sending serial data down, you can say, "Wait, I'm not ready for any more data," or "Okay, I'm ready." I think that's what the B pins are for. Is like a flow control pin that tells the host or the master to like wait.
Okay. So this is feedback from the chips to the host saying, "Okay, just wait. I'm busy," or maybe B is for busy.
Maybe busy. Yeah, it's got an input and output, so we can cascade that.
Yeah.
In practice, I've never seen those pins do anything.
Oh, but you've seen them connected, right?
Or
not connected.
So I have connected it to the microcontroller, this BMBI. I've connected it to the microcontroller. One of the guys on the forum was had some theory about what we could do with that, and I was like, okay, I'll hook it up. We got extra pins.
Okay.
So I think I think I had an issue where it wasn't working, and I had to either pull that pin high or low to get the chip to actually start mining. So I think it might be an input
Interesting
flow control, like a
okay. Dude,
like maybe
there's a whole sub community that's going on here about understanding and R&Ding. This thing is more than just this thing is an R&D device, really. I mean,
oh yeah, oh yeah. Some people have like messaged me and they'd be like, oh man, I really want to like do some mining, and I'm like, you
yeah,
should get something else because that's not where we're at yet. Maybe soon, maybe soon.
this is
But
cool. But I like it.
yeah,
I like it. I like it.
it's like if you want something to hack on and maybe learn a lot and or get really frustrated, this is the
This is
process.
where it's at. Yeah. You've got a reference voltage regulators over here. Okay, so these are connected to.
These are connected to the IO voltages. So this is 1.8 volts, this guy here, and this one's 0.8 volts.
Oh, I see. Yeah.
So
Okay,
those
keep
take
going.
that 5 volt. Remember you were asking me like that 5 volt output from the other block, where does that go?
That's right.
That comes into this block and powers these reference voltage regulators.
Oh, I see. And
So
then
it's really current, it's just a reference voltage.
okay, okay, okay. But that and this and
It goes down here.
that's right. That's right. There you go. So there's a V8 and then yeah. So it's on pin 14, 15, and 16 over there, and then that just gets relayed straight out again. So you can does it
It just goes right from these
chained right
voltage regulators here. It goes right to the chip. That's it.
Okay.
These are bypass capacitors here, just to remove noise from those voltage rails. But the chip just requires those voltages to operate.
Okay.
Like power domains.
Yeah. Okay. Fascinating. Any other bits of info? Well, what's it? What's U3 bottom right?
Okay, so both of these things here are level shifters.
Okay.
Like I was saying before, the chip, the VM131397, operates at an IO voltage of 1.8 volts. The microcontroller I'm using doesn't operate at 1.8 volts. It's 3.3 volts. So I have a level shifter here for all those signals we were talking about to connect into the microcontroller. And this one here, we added this with the idea that the microcontroller could also provide the clock signal to the mining ASIC. Instead of this fixed 25 megahertz clock, we could use a peripheral on the microcontroller to send that clock signal, with the idea that maybe we could do a little bit more tuning by adjusting that clock.
I see.
So that's on there and it's hooked up, but I haven't tried it yet. That's just kind of an idea. It was easy enough to do.
I see. Okay. All right.
And this is also a level shifter here, but it only had 4 channels, so we needed another one for this.
I see.
This part, however, is a bidirectional level shifter, and I've come to realize it's not so hot. I actually don't like it. I think in the future I'll put down 4 more of these single direction level shifters. They're just a little bit more stable.
Okay. Stable is in voltage.
Stable is in their operation. I got into a situation where I think this level shifter was oscillating. Like it just got.
Oh.
I mean, essentially, it got freaked out and it stopped doing its job.
I see. That's not fun. Okay.
Yeah, and this particular part is a little bit infamous. There's some other people on the internet that complain about the same thing happening to them. So
okay. So if you just go with the SN74A, then like times 4, and then that should keep things exactly more stable. Is the part more cheap? Okay. We don't have to go into the cost of the parts. Are we done with this?
It's pretty cheap stuff, but they do go out of stock, and so that's also a pain in the neck, right?
Yeah.
But there's a lot of level shifters. There's a lot of different parts, so we can kind of put new ones in there as stock changes. Yeah, so that's what this whole section is. This is a debug header over here. Up here, just more bypass capacitors. This is a pretty big cap right here.
Why is it so big?
Well, it's a large capacitance, 330 microfarads. And the physics of capacitors is the higher the capacitance, the physically larger they are. Right? Like, all the rest of these are like 1 microfarad, and this one's 330. So if you look at your board, you can see it's they need to be physically close to the chip. So if you flip it over, it's on the backside of the ASIC.
Yeah, directly on the backside, right? Exactly.
Directly on the backside.
And this is the massive one over that sits over here, right?
Yep.
Yeah.
Yeah.
We'll go into the PCB layout because there's some interesting stuff there. Some like stuff I've never seen before. But I mean, because I'm very new to this, but you've got these massive power rails. It's just just huge. Let's go on to the next schematic.
Okay. So maybe we'll just pop into this one. This is the fan.
I was going to suggest we do the fan because I've got some suggestions to do on the last one. Okay, keep going.
Okay. All right. This is a fan controller. I found this part. It's from the PC world, and it's the perfect part because it is a I2C fan controller as well as feedback. So over I2C, I can say set the fan to 50%, and then it also measures the fan speed so that you can like confirmed it's moving, right? Because if that fan stops, you need to turn this thing off right away. But not only that, it also has the ability to measure the temperature of that internal of the ASIC's internal temperature sensor.
Oh, cool.
And digitize that and it back over I2C.
Oh, so you got a very nice, you got a nice feedback loop there. It's good.
Yeah. So it's meant for this, and it can even run its own little algorithm. You can do set points in this chip where you say, like, if the temperature of this chip, gets over this, turn on the fan 100%, or little algorithms like that to try and combat heat problems. It has this like alert pin, so you can that alert pin can tell you like temperature's out of control or fan stopped working or something like that.
Let me ask these questions now as we're in the fan section. So the micro inverters on solar panels. What they do for a number of them, they actually put them in a potting compound. And it's like almost completely sealed, and it is completely sealed, and it's entirely waterproof. And the reason is because this component is out there in the elements, right? So it has to be pretty robust to the elements. Now, the thing is that I've been thinking about this, like, how the hell is it going to happen? How are you going to disseminate, get rid of the heat and at the same time retain the whole robustness against the elements? Is this where the heating pipe comes into it? I mean, you just stick a heating pipe directly into this potting compound and then goes down into the earth.
Yeah, I mean, that's what I was thinking, right? Like, you could imagine a heat sink that is thermally connected to the top of the chip, and then you pot it essentially on there, leaving like the top of the heatsink or most of the heatsink exposed, right? So no water can get to the circuitry or the chips, but because this heatsink is thermally coupled to the ASIC, we can still sort of extract that heat out of there. Doesn't help with the fan, but maybe if this heat pipe idea works, we could do that. I think.
So the direction would definitely do the potting, is that right? I mean, I assume that it has to be this way because you want it to be robust against the elements. So that's a invariant. The potting would be an invariant.
Yeah, I think so. And I've arranged to have a circuit board potted before. You just get a PCBA shop and you give them the specs for what you need, and they make a little mask. And there's all kinds of different potting compounds and things. There's everything from like a thick goo to like a thin spray, to make it, differing levels of waterproofedness. And
surely there would be a nicer one such that it's also waterproofing but also thermally conductive, so you can actually move the heat out from the entire board itself. We can actually assist in distributing the heat.
That's an interesting concept. There's got to be something, right? We're not the first people to run into this problem. Like
exactly.
Something from the automobile industry.
Sure.
Everyone wants to not overheat and to be out in the elements.
Exactly. So I think your heat pipe idea mixed with a thermo moving, I don't even know the word, but a potting mixture that which can actually move heat. And then at that point, you just have a couple of heat pipes in there, maybe take it down to the ground. That might do it, but it's going to have to be a lot of testing too, eh?
Yeah.
Especially, imagine for a second now I go to Namibia, which has some of the highest irradiances in the world, right? And the temperatures in the desert just go straight up, like massively, like, gosh, you have a lot of heat that needs to. But in that situation, it'll be behind the solar panel, right? Maybe the air temperature will be quite low, relevant because it's not getting direct.
Yeah, right. It's not getting that radiative heating, right? It's only getting the convection heating from the ground, and the air, the hot air around. So it should be less, right? You leave like a metal box out in the sun, it can get scalding immediately, but in the shade, it just gets uncomfortably warm.
Yeah. So heating's a huge issue with this thing because of it. It's out in the elements. Okay, so
put the whole thing underground. I don't know, right? Like,
dude, fucking hell! I never thought about that. That's great.
You still got to get the heat out, right? Because the ground's
not a good
conductor, but maybe that's easier to get the heat out rather than sort of get the heat in the ground. I don't know what I'm talking about here, but it's fun to think about.
No, I think it's good. I mean, also, if you imagine if you've got a heat pipe that's running down the length of the stand, right? And if it's on the outside and it's going to get some sun, you're heating up your chip because the sun's heating up the heat pipe. You see what I mean? Damn it.
But like, I'm sure that they have a good reason, but I don't know why they put the solar panels so high off the ground, right? I mean, couldn't you mount the solar panel a lot lower to the ground? Maybe so it doesn't get dirty or something?
Yeah. Well, I mean, I imagine animals walking over it or human beings walking over it and they crack and then fuck.
Yeah.
The circuit is broken. No, solar panels are a flaky thing. So when I always get amused whenever I see these people say, "Oh yeah, we're gonna put like solar panels on the ground or like on railroad tracks." It's like, fucking morons! Don't do that. Solar panels are very, very sensitive to vibrations. One crack, you're done.
Oh yeah, right. Yeah, you have to spend so much time like protecting it and making it more rigid.
Yeah, like, exactly.
Gonna blow all your like cost.
Yeah. Oh, interesting. Okay. Shall we go to the next section now?
Yes.
Any more interesting parts you want to talk about in the fan section?
Nope. There's just the fan connector right there with a couple of bypass caps on it. Fans are pretty noisy. Yeah. So let's go on to the ESP32.
Cool.
Block here. So you can see we got all the data lines from the ASIC coming in here. We got I2C and some different power rails coming in.
Yeah. And your fan alerts,
This is the brains of the operation and the part that I've done the least amount of work on. I was just kind of putting that off till the end. But I've met a couple of people that are interested in working on this, and I want to start working on it soon. But I know that I did sort of the initial bring up, and it does work. So that's a good sign. We got an ESP32S3. This is kind of the latest and greatest ESP32. ESP32 is a popular 32-bit microcontroller that has Wi-Fi and Bluetooth built in, has a bunch of flash storage built into it. It famously does not use an ARM core, which makes it very cheap. It uses a Tensilica core, but when you never know the difference when you're programming it. That's all sort of abstracted out in the library. But yeah, it's cool. The story of Espressif and the ESP, the previous one, is pretty interesting. It's kind of from a.
Let's hear it.
What's that?
Let's hear it.
Okay, so I think maybe 10 years ago, maybe.
Right.
The sort of Hackaday crew, so the DIY electronics crew was like, we just found this really cheap Wi-Fi microcontroller online, and there's no documentation about it at all, but it's really cheap. It's like just a couple bucks, and like this is huge. It was ESP like 8266, I think it was called, and people were starting to flip out and like trying to reverse engineer it and trying to translate data sheets and things like that. Like the company Espressif is in Shenzhen, I assume, and documentation was minimal, but it was cheap, and the hacker community kind of like took it on and started working with it, and like a lot of it got documented. And around that same time, Espressif, the company, hired one of the editors from Hackaday to actually like help them get this out there, and it was nice because apparently Espressif, the company that makes this, they did want to like get the documentation out there because they wanted to sell more chips, unlike someone we know. So they got it out there. They released this new version, the ESP32, which has had a bunch of different revs, and it's really cool. It's really, really cool. There's tons of awesome projects for this. Tons like you can get Arduino libraries on here. You can go nuts with this thing. So it's a super like hobbyist friendly, popular embedded system. And it's nice because it has Wi-Fi and Bluetooth and a ton of other peripherals in it. And it's like a couple bucks.
Mm. And you chose this because of the Wi-Fi, right?
Yes. I chose it because of the Wi-Fi and just its general like popularity with the open source hardware crew, I guess.
Okay. Now you know what? I'm gonna let you explain the chip, and then I'd like to go into my
sure.
my
Okay, I can
points.
tell you got some
Okay,
thoughts about this. This is good.
cool.
So one more quick embedded systems geek story.
Okay.
I originally wanted to use the ESP32C3 instead of the S3. That is a very cool part because it's a RISC-V core.
Yeah,
and RISC-V
it's all
is
the rage these days, man.
An open source processor. The ISA and everything is fully open source, and it's slowly taking the world by storm, right? Because we have this, Intel with x86, and we have ARM, which is sort of the underdog, but it's pretty cool. But they're still like, closed source, and you have to sign away your soul to figure out how that processor actually works. And then we have RISC-V coming along, and it's open, and there's like some people are starting to make desktop systems and some embedded systems like this, and it's still pretty early days, but it's really cool, really promising. And the ESP32C3 is a microcontroller platform just like this, but it has that RISC-V core in it. And so my first versions had that, but unfortunately, Espressif does not make a version of it that has enough RAM to support some of the string processing that we need to do on this thing.
How much RAM do you need?
Oh, I think it was like 300 kilobytes on the C3, and this has like 2 megabytes.
Uh-huh. Okay.
So, it's like maybe with a lot of hacking and optimization, we could have made it work, but I was like, I'm just trying to get this thing to work, so I don't want to be screwing with that just yet.
Yeah, and also you don't want to be locked into a corner.
Yeah. So, this thing needs to talk Stratum, which is the protocol by which miners get work, which is an ASCII, text format. So that means that this processor is going to have to deal with a lot of big, long strings in RAM. So you just kind of gotta, I don't know. It's easier if you just have a bunch of RAM.
I hear you. I hear you.
So it's got the S3, which is a 10 silica core, which is not open, but still cool. Yeah, so that's the processor. What we've got on here is 2 RGB LEDs. This was some random guy that I met on the internet was like, dude, you got to put some LEDs on there. I said, okay. All right, let's do it. So we got RGB LEDs on there. And we have, this is just another voltage regulator to get the 3.3 volts for the processor. Crystals, we got two. This is the 32 kilohertz crystal that's used for situations where you want to keep like real clock time.
Yeah.
Because 32,768 is exactly 2 to the 15 bits. So it divides evenly into 1 second. JTAG programmer connection here, big old debug header here, a tag connect programmer here.
Yeah.
That's that weird.
Yeah, it's how you program the ESP
corner of the board. Yeah, it's like a connectorless connector. They make a little.
This one?
No, it's in the upper left.
Oh, up this one.
On the other side, it's like 6 pads with just surface mount pad. Yeah, that's it up there.
Wait a second. Is it this one? This tiny little one over here? Oh, shit.
It's got those 3 holes and the 6 pads.
Yeah. Okay. I got it.
So there's a connector that you can buy called a tag connect, and it will latch onto those pads. It has little pogo pins and little snaps, and it just snaps on there. And so
no soldering.
No soldering. No, you don't have to put a connector on there. You don't have to pay to put a connector on there. So the cable, that little cable is like $30, but then every board you don't have to pay to put a connector on.
Yeah,
that's sort of their angle. Okay. I got a pull request on my GitHub the other day to remove that. Someone was not happy about it. But it makes sense if you're going to make, if you're paying 50 cents for a connector, as soon as you make over 60 boards, now you're saving money with this.
Yeah.
So anyways, that's for programming the ESP32. You have to use I don't have it on my desk anymore. You have to use an ESP prog. It's a little USB programmer.
Yeah. Oh no, it's in my yes, that's right. It's a little thing.
It's like
I got one too.
Yeah, it's a good thing to have if you're hacking on this stuff. It's like $12.
Yeah.
Let's see. So this is a pretty standard layout for the ESP32. I've got another one of those solder jumpers here, depending on how you want to change the tag source. Crystal connections. There's JTAG over there. This is the serial port that comes in over this tag connect for programming it.
Oh, yes.
Here's that clock pin. Remember I was telling you about that experiment to see if we can clock the the ASIC from the microcontroller. That's that pin. That's level shifted.
But that experiment is not done yet. It's just there. Yeah, it's just there at the moment.
Yeah, it's just wired up. There's a little resistor that you can take off that disconnects it, like a 0 ohm jumper resistor.
Right.
In fact, I actually need to put that in the README that you should not have both the crystal oscillator and the ESP32 connected to the clock. It won't work.
Get the to-do list.
Yeah.
Yes, no, the thing will break, but you can just desolder it, I suppose.
Yeah,
and then you get.
Yeah. It's it is.
There it is, the R2, right?
Yeah, is it that one? No, it's not that one. Here, it's this one, R23. So if you take this
Oh,
off,
do not place R23 if using 1U oscillator. You got a comment there already.
There we go. Yeah, I
uh,
should call that out. That's more important. Okay.
okay.
Back over here. Okay. So yeah, here's kind of the meat of it, right? This is the data connection to the mining ASIC. It's just a serial port. It will accept serial data at like 3 megabaud, or I've heard actually can do 12 megabaud. So this is like pretty fast for serial, right? This isn't your like, 9600 baud serial stuff. I have not tried to max it out yet, but that's in the to-do list. Because if you can send work to these miners faster, then you have a better chance of keeping them always loaded with new work to do.
Yeah.
There's that BI pin. We have a power good output from the voltage regulator. It just says, yeah, the voltage regulator is up and running.
All good.
That's that fan alert pin.
Systems are nominal.
Yeah, exactly. Here's that reset. It's a reset, goes to the NRSTI.
Relays it, yeah. And then BDD.
Okay. Here is this pin, BDD, that is connected to a voltage divider that goes to the it's connected directly to the output of the voltage regulator and to an ADC, analog to digital converter input on the microcontroller, so that you can monitor the output voltage that's going to the ASIC from here.
Okay.
Yeah, that's this sort of closed loop control kind of stuff. Yeah, let's see. Is that it? I think that's it. There's the LEDs connected up there.
Yeah, there's and then also on the right side, you've also got the LEDs.
Right, we got RGB for both LEDs. There's like PWM peripherals inside the ESP32, so you can like fade it and do cool colors.
Oh, okay, cool. What about this MTCK, MTD0 bottom right?
Those are JTAG signals.
Oh, sorry. Oh, I didn't know. Okay.
Yeah, that's new on this rev. I didn't have that before, and I wanted to put that on there because I wasn't sure if you can do like proper debugging over this
interface.
Right?
I see.
Just the serial bootloader interface. And I think you might need this JTAG to do proper debugging. And the ESP prog has a JTAG port on it, so you can just plug that right into here. And,
you can get your data out, so you can see the execution of your
program. You can like halt, you can single step through your code, like all that good stuff.
Yeah. Okay, cool. So now maybe I can.
I2C is over here.
Oh yes.
Those you actually don't need those pull-up resistors. I gotta pull those out of there because
why don't you need them?
I mean, you need pull-up resistors for I2C because it's a open drain. Basically, the I2C lines can only be pulled down to ground, and then they go floating, they go tri-stated, and you need a pull-up resistor to pull it up to register like a 1, like a digital 1. But the ESP32 has configurable pull-up, pull-down resistors on every I/O pin. So you can just use those, and you don't need to have these external ones.
Oh, I see. Okay, so you can configure the state in the chip itself directly.
Yeah, it's pretty cool. Like, I feel like modern, like cool microcontrollers, they'll have that. It's a nice touch.
Yeah. Oh, we've touched all the different components now. How about, have you got the firmware running for this? What does the firmware look like? Oh, wait. Yeah. Yeah.
I have a firmware on GitHub that does everything except for mining.
Right.
So it can control the fan, it can control the mining core voltage.
Cool.
It can do all the I2C stuff. It can measure the temperature. It can do the power monitor to see, how many watts you're pulling. basically all the peripherals, everything but mining, right? And
Cool.
that mining is a bigger job and haven't finished
Huge,
that yet.
huge important step there.
Yes.
That's really good. You can get all the peripherals working. All right, let me bring in my thing. Okay, one of the primary reasons why this project interests me is because I have a sort of like, it's almost a decade long ambition, is to create a means for people to communicate via an addressable entity that they control themselves. So I like Bitcoin because Bitcoin, you spin up your own key pair, and then what happens is I create addressable financial addressable entities that I control, and nobody else can control. So now I have self-sovereignty over my financial world, right? I can communicate with you in this podcast. I can give you my Bitcoin address, and then you can send it to me in this completely different payment rail.
And there's nothing that anyone can do about it, right?
Nothing anybody can do about it. That's correct. But that doesn't really exist in the data world, because the IP address that is allocated to you is not owned by you. It's controlled and owned by somebody else. And during times of war, the IP address can be controlled by the state. So if they don't like you, you're done. If some state decides, like, if you want internet access, you have to have some sort of a digital certificate, etc. So they can add layers to this ability for you to communicate. So for me, what I see as important is to create a key pair. Basically, you spin up a key pair, and actually, I should sort of speak about this now. This is kind of like a little bit of an ongoing project. I'm creating it now.
Nice.
What you see here is this is all like recently created. I'm
I want to
dude, I'm going
so I can see.
Okay.
Okay.
Say.
You hold it up again.
I see. Do it again. Do it again. Okay. So
yeah.
What you see here is it's
Okay.
this is the base layer of this system that I'm creating. What you see is two D16 dice, D16, 16-sided dice. It's times 2. You've got a metal plate with let me go in closer. So you got 32 bytes of information.
Okay.
On a steel plate. This allows you to.
It's a serious steel plate too.
Yeah, no, it's a SSL. The marine grade steel, and then you've got a heavy duty center punch, and then you've got an STM32, which does the conversion which helps you convert dice rolls into the binary representation for you to stamp it out.
Okay.
And then it converts the binary, all 32 bytes, into a BIP39, the words, the seed phrase, right? So that allows you to now
completely offline. You can create a wallet.
Yes, but it's not using, what they say, not your random number generator, not your Bitcoin. So this process says, okay, fine, then we're gonna use fucking dice to create our own identity. Now, this identity you persist on a metal plate. Yeah, shove it up your ass when you want to walk across the border. It can act as your Bitcoin key, but also this is where it comes into it. It also acts as your digital identity. So the next layer of stuff that I'm building is a new internet protocol. I've actually created one already as a proof of concept. It's called Copernica, whereby you can spin up your own private key, public key, and I can communicate with you using your public key as an addressable source of information. Right.
Oh my gosh.
Now, that's very inconvenient to use. So I'm okay, hear me out. I'm creating a programming language which is built on top of this information-centric protocol, right? Yeah. Which allows you to so every variable will have its own sort of addressable information. Every process, lightweight language process, will have its own key pair, which is derived from the master key pair. Getting complicated, but
Yes.
this virtual machine is designed to execute directly on bare metal. And the reason for that is because it is a capability secure programming language, and it's going to be it's going to be able to create Bitcoin transactions. And I want to reduce the attack surface such that there is no operating system. Okay. Now, the next thing is I want it executing on things like SDMs, on ESP32s, etc., because how else are you going to create an alternative backbone of information? The best way I came up with is solar panels, because solar panels, I can stick a solar panel on the mountain over there. It's independent. It's got its own power source. And if I use LoRa, now I can communicate kilometers at a time, right? So I can start relaying information using this internet protocol, which executes on the virtual machine that I'm working with, right? This is quite interesting for me, because now suddenly a farmer in America, he might think, you know what, I've got loads of space. Let me create a little backbone of solar panels which connect one end of my farm to another end of my farm. And then the same happens with another farm next door. So what happens is you start creating these chains of information of LoRa connected solar panels running running the virtual machine. It's called CO, Secure Input Output. That's the name of the programming language I'm creating, CO. And this is where I would like to see Bitaxe come into it, because what better place to put this? The thing is, it's not going to work with Wi-Fi. It won't work with Wi-Fi. It has to be LoRa.
It's like IP to the core, right?
Exactly.
Well,
that's exactly it. That's the issue I've got. And so I love the Bitaxe concept, but my main issue here is that using the ESP32 does not allow me to fulfill that vision. If, on the other hand, it's using something like an STM32 or the cheap Chinese knockoff, the GD32, along with LoRa, then you can start to create these peer-to-peer sort of networks, which allow us to create sort of even backbones of information that relay this information across entire countries if needed. So what's the probability of the ESP32 being swapped out for, and also ESP32, it has its own sort of what's the word? I forgot what the word is, but LLVM doesn't really support it on mainline. Maybe it's changed, but you actually have to use a separate LLVM to get this to work. Whereas like in Rust or Zig and other programming languages, if it's the STM32, you get it out the box. It's immediately supported.
You're right. You're right. Yeah, they have that. I mean, I think it's still GCC, but they have that ESP IDF framework, which is a little bit obfuscated. I think there's actually for the Wi-Fi, I don't think the source is provided, so it's the whole stack there is closed. That's some of the criticism the ESP32 gets. So this could totally work with the ESP32 or with the the STM32 and a LoRa transceiver, right? And I think they actually make some now where it's both of those together.
The Murata. He's got like a content chip.
And Seed Studio makes a cool one. Where
is my board? I've got a Murata right here.
Okay.
Let me just quickly open. Oh, I just muted you. Okay. This is a.
Oh yes, nice.
Yeah, this is the
one of those as well. Yeah.
Oh, you do you? Okay.
Yeah, I've done quite a bit of LoRa stuff for my day job. It's fantastic.
Do you think it'll be able to handle the amount of traffic that's needed for mining?
Um,
If
I
it's
think
not
we would,
ASCII, you'd have to go to binary at that point, right?
yeah, I think we would probably need to develop a new like stratum replacement protocol.
Yeah.
But
So this is where I'd like to put it. Actually, that would be implemented in the CO programming language.
yeah,
In my
yeah.
the way I've got it, you see, CO actually would be like, I'm sure you're familiar with MicroPython, right?
Hmm.
So MicroPython, you just flash it directly onto the board, and then you can actually control the peripherals from there. The idea is that I want CO to be a similar sort of MicroPython, except that it's got the capability secure. Capability is secure. Do you know what that means? It's basically the keys are actually first-class citizens within the programming language. So
Oh,
if you have a a process, are you familiar with Erlang?
only the name. It's a
Okay.
programming language.
All right. So imagine spinning up a process, an operating system process, but it's not an operating system process. It's a language virtual machine
Okay.
process. Okay.
Okay.
And every single
It's
process.
like an interpreter, right? That's like MicroPython is an interpreted languages, right?
That is correct. Now imagine inside MicroPython you can spin up a MicroPython process, which is its own little executing time sliced process which can run, and it
Yeah.
can have its own threads inside it.
Hmm.
Um, but the key is that every single process will have its own key pair. So
Oh,
when you want to communicate information from one process to another process, process number one needs to know the public key of process number two. And process number two must know the public key of process number one. So that when you send information, process number one will encrypt the information, even though it's on the same virtual machine. The information will transfer to process number two, and then process number two will decrypt it and then continue the process. So the idea, that's my interpretation of capability secure inside this particular programming language that I'm designing, creating. But the point is that
so why would you want to do that, right? It's all on the same chip.
Excellent question. So, yes. Well, first of all, if I'm communicating, yes, you can do that. I know that. I understand that. But the thing is that because it's an addressable space, it doesn't have to be. It could be. It could actually communicate outside elsewhere. There might be other
Okay.
consumers of this
So these
information. Yeah.
sort of inter-process communications could happen over, they could be just in memory on the same chip or through an untrusted LoRa link across town.
Bingo. So one of the success points about Erlang is this lightweight language processor, is that it does not differentiate, but distribution is not differentiated between processes inside a virtual machine or across a network barrier. That's what makes it much easier to
Okay.
so the boundary, you just say, the boundary is the process. Anything that leaves the process, we consider it hostile territory, whether it's on the same virtual machine or it's across open internet. Now, the good thing about this is that this process, by using addressable public keys, I now don't give a fuck about the transport I'm using. I could use LoRa, I could use Wi-Fi, I could use TCP/IP, UDP, I can use Bluetooth, I can use whatever. It doesn't matter. It's just an overlay.
Mm-hmm.
Now, to fulfill the vision of creating backbones of communication communication backbones whereby people control their own addressable endpoints, the solar panels along with LoRa is the right way to go, because now I can communicate 10 kilometers now, as opposed to I think it's a design flaw, basically, what I'm trying to say, by you choosing to use Wi-Fi, because Wi-Fi you can only go so far for your fleet of solar panels can only go so far. But if you got LoRa and you got the right protocol, you can create like a bridge. For example, let's say I own a land across this mountain over here. But I don't want to put my backyard full of solar panels, right? I can create like a relay,
Yeah.
and then my master node is sitting at home where I've got a high bandwidth connection. I can got my main core node, which is getting all the work, and then translate the work into CO, and then ship it off to my solar panel farm to do the work, and then the work will come back to me via this means. So I can actually relay it over LoRa, and then the work gets distributed, and it can come back. You're not going to be able to do that with Wi-Fi.
This is a good idea.
Yeah,
this is a good idea. I like from like a high level. I think about that a lot too, because the internet is a weak link in Bitcoin.
Yeah, very much so. This is state controlled.
Yeah,
like,
yeah, power is obviously also a weak link, but solar panels, right? Like this is the permissionless energy that we need. So, I guess I don't fully understand like how you're going to be able to do that, but I think on a higher level, like, being able to do this on long distance, sort of untrusted links of whatever type works best for the situation, is going to be huge, right? We've got to have this.
Yeah,
we've absolutely got to have this.
So,
when I originally my first thought for the Bitaxe for the wireless was going to be one of those 802.15.4 like mesh networks. And I bought the TI dev boards to do it. And I was like, what am I doing? Like, I have so many things I need to figure out before I do that. So I shelved that idea, but that was the original intent, right? Is to do that. My goal was in not using Wi-Fi was that there's going to be a ton of these things in a pretty small area. And you can't have just like 10,000 clients on your Wi-Fi network.
No.
So you need something else that can support that. So that's where I was going with that. But I think it could work over LoRa. LoRa's fantastic. I worked on a project that was doing LoRa to space.
Bro, it's totally possible. It's absolutely possible to do. This is why I'm like, now, okay, let's open that little chapter. Yeah, you go straight to space, and then you relay this LoRa shit between the satellites around the world. And now I'm talking to a solar panel farm on the other side of the world. It's fucking insane, this technology.
Yeah,
I love it.
Yeah, it's really cool. It's because LoRa is a modulation scheme, right? That allows you to transmit with less power because it's better at extracting the data from the noise. So
because of
you
the
can
chirping.
do LoRa. Yeah, that's right. They have those chirps.
Yeah.
But like, for example, this company that did LoRa to space, they did it to little CubeSats, right? It was like tiny little satellites.
Awesome.
But they use that modulation at 150 megahertz, right? Like, the LoRa that you might normally get is like 900 megahertz, or I think they have 400 megahertz. But so it was kind of interesting because they needed to get, I forget the altitude of low Earth orbit, right? But this is like, it's thousands of miles. So they needed to get quite far, but they did it. It works. Like, you can do it. And LoRa modulation is incredibly versatile. And they spun this up like pretty, bootstrappy, like pretty bare bones, right? It's not like you needed a lot of permission to do it. So it's a fantastic way to do this. I think with some effort that you could probably get a stratum replacement working over LoRa, right? It's incredibly low bandwidth, but the other problem is latency too, right? Like if you have a bunch of hops, you're going to add a bunch of latency to your link. So
you can't avoid that. I mean, that's physics, right? I mean, you can make it as efficient as possible, but I mean, if you've got your workhorse on the other side of the mountain, not much you can do about that.
Yeah, the latency, especially when you're like say your mining pool or your miners just found a block, right? You need to broadcast that to the Bitcoin network as fast as possible, assuming that the whole internet hasn't been shut off.
Well, yeah, that's exactly that's a really good point. I mean, assume like Bitcoin was designed for where the state is the ultimate threat actor, the threat model, right? So like we're all used to this world now. It's all very good and well. We can do this conference right now, but when wartime situation happens and all of the stuff goes away, all of it fucking goes away. And what are you left with? Well, you've got things like LoRa. You got, I know there's a supply chain for LoRa and all of that sort of stuff, but if enough of the devices are out there and people are just saying, well, we can communicate via this mechanism already, that puts the citizens in a significant position where they're able to communicate, not at the behest of the state. And do you see what I mean?
Yeah, like we've gotten a taste of this, like completely permissionless.
Yeah, I want
method
more
of interaction with Bitcoin, right? And it's like, oh, that's good, right? That's real good, right?
Let's have more of that. Yeah.
Yes. Yes. So I mean, I'm fully on board.
Cool. This is really good, because now I don't have to create this, because I was tilting at this windmill, man. I was full tilt at creating one of these things. And now that I've spoken to you, there's a sane head behind this project. There's good engineering decisions that have gone into this. It's like, now maybe I can just focus straight on the virtual machine and use this if and only if it's the STM32 along with LoRa. Because if that happens, then I can just focus all my attention on just creating the CO, which will be the control system which runs on this board. And then I can build up the programming language from there and build up all the shit that needs to go into that stuff, it's a lot. It's a hell project, but it's fun.
Yeah, it's a lot.
But at least
this is the goal, right? Well, this is the goal of the Bitaxe, right? It's like, may like 1,000 new projects bloom, right? Like,
yeah, exactly.
There's so much opportunity here, right? You get these people on Twitter, like Troy Cross and like some of these other people that are they're so good at like coming up with how this is going to change the world and all these like amazing applications.
Oh, those guys. Oh, I thought you talked about the naysayers. Oh, sorry.
Oh, no. I'm talking about the yaysayers, right? Like, like all the, all the people that are tons of followers and they're just like preaching Bitcoin and all the good things it can do for the world, right? And it's absolutely true. I fully drank the Kool-Aid, right? But we don't have the hardware to support these things that they're talking about, right? Which and what you're talking about, right? So that's the hope, is to like start that maybe in the smallest way, right? But like, Linus Torvalds just wrote the Linux kernel, and then a bunch of other people worked really hard on a bunch of stuff, and like, look where we are. This is fantastic. Like, open source software is huge. It runs the entire internet for all its faults. Like, so yes. So what we can do is this. Like, I'm going to write the firmware to do the mining for ESP32, but it's in FreeRTOS, which is available for STM32, and I think it's what the examples for communicating over LoRa use. But it's all going to be open source, and in hopefully it's easy to understand C as I can do. So you can totally incorporate that on a STM32. I can help with that too.
All right.
It'll work just as well on an ESP32 with a different sort of networking backend, as it does on the ESP32, right? I'd really like to abstract that sort of network interface from the miner as much as possible.
Yeah. So yeah, okay. You keep plugging on with the ESP32. I don't want to. It's like there's a lot of stuff that's in motion at the moment, and I fully understand. Like, don't put that thing on my shoulder now. It's like I've got a whole bunch of other shit to deal with. But yeah. So like, I hope down the line it might be interesting. Like, if I get something nice working, maybe I could make a patch and then swap out the ESP32 with the STM32 or the GD32. That could work. Would that sort of thing work well if you were to if I were to create a, well, when I mean that, I mean the whole virtual machine, the control system also in place. I think I would probably fork this thing, make the changes I need, and then use it as a dev board. And then once I get things working, then maybe you can assess whether it's nice, and maybe it can be introduced into mainline or not. Up to you.
I mean, I absolutely think it can work, right? There's like a big block of heavy duty work in between now and this,
yes. Oh, very much so. Very much so.
But it sounds like you're interested in doing that. So like, I think, the things I can help with are the interface to the ASIC, right? Because there's all these registers, right? The driver.
Right.
The driver isn't going to care if it's run on STM32 and ESP32 and MSP432 or anything else. So I think that can be really useful, right? And the more modular that is, the easier it'll be for you to drop anything else.
This is great. Cool.
I have like the KCAD parts, for a bunch of STM32 stuff. I've worked with them a bunch before, right? So we could totally slap that on there and spin up some boards if that's what you're like looking for help with. I think
my initial goal was to bring this to completion, and then get because I've decided to use Zig and not Rust. Rust is just optimized for speed but not size, whereas Zig seems to be optimized for, you can optimize it for size. So I can get I can get a nice program, that the entire virtual machine and the router and all of that stuff. I can write it all in Zig, and it can be optimized for size for these small devices, which is something that I need. And then I was just gonna make it work with the ESP32, just as the board as it is.
Do this. You can build that board and just don't put the ESP32 on there. And there's pin headers for all the signals that you need. So just use little jumpers and go over to your Murata STM32 LoRa dev.
Oh my God. Okay. Yeah. Just like a side by side.
Yeah. No, that'll totally work.
Oh, interesting.
Seriously, just don't solder on the ESP32. And then you can use those headers. I have headers for the level shifted, all the signals.
Cool.
We'll go right over.
That's a great idea.
Right, we'll go right over, so you can control the fan and the ASIC core voltage, right? And this will totally work. You should develop it on the ESP32. And
the STM32.
Right, yeah. Gosh, you should develop it on the STM32.
And that's a great idea. I'll just do that.
A few jumpers, right? Like,
this is a fantastic idea. I love it.
The pin headers are on there. This can totally work.
I'm excited now. Great.
And then you just need to, once that's all working, then you figure out, it's not going to be that hard to change out the ESP32 in the KCAD design files for STM.
Yeah. Brilliant, man. Look, we've been speaking now for more than 3 hours. That's
holy cow.
Yeah. They go quick, eh? Dude, we haven't even looked at the PCB layout. We haven't even done that. And maybe we could do that just about like very briefly. Like I like if there's any interesting stuff, like I really, to me, that's quite important to understand a little bit more about how you did the layout. And do you want to take the sharing again?
Yeah, let's do it here.
I can see you getting a little bit tired.
I love talking about this stuff.
Good.
Like almost 10 p.m. here, but whatever.
Your wife is going to be, come to bed, darling.
Yeah.
All right. Are you sharing it? You got it?
Wait, hold on, sharing. All right. How's that look?
There we go. Okay, lovely stuff. Right. Now we're looking at we're on the silk
Yeah. All
stream.
right. So this is the board layout. There's some fat traces. Like this one.
Absolute
This one.
monsters.
Yes. Just fat traces. They're not even traces, they're polygons. I just drew big polygons because it's like, this isn't going to be like a 10 millimeter trace. So just draw big blocks. And those are the high current traces, right? Like when you're doing board layout, right, and you have high current, you need to have thicker traces, wider traces, more copper.
There you
So
go.
let's see. I guess I don't know. I'm going to show this. Actually, I wonder if there we go.
That's it.
Okay. So this guy here is the inductor. These are the power MOSFETs. And that's a capacitor. But basically, that's the switch mode regulator, right? That's where all the juice flows. These are the inputs here, power and ground.
Yeah. Mm-hmm.
And it's just, you want to have a short, fat trace. It goes through the power monitor here.
Mm-hmm.
That chip. Oops, that one. And yeah, it just short, fat flows over to the switch mode regulator, and then goes straight down to the ASIC, which is right down in here.
Yeah.
It's on the other side. There it is. That guy.
So through a bunch of vias and then straight down to the.
Yeah. So what you can't see on here is this is a 4-layer board. So I have a big fat internal power plane and ground plane. This is the
Isn't that particular configuration can create high inductance? Oh, I forgot. I remember learning about these different power planes, and and then the signal, ground, power, and then signal again. It doesn't that cause problems?
You can get a bunch of parasitic capacitance.
That's the word.
Yeah,
that's the phrase.
Yeah, that's an issue, right? And you have to also look at like return path length, right? So if you have
that's the issue. Yeah, exactly.
Yeah.
So how are you solving this?
Over a different path length, then you can have a little bit of voltage drop over a single plane, and voltage difference in parallel plates is a capacitor. So I don't run high current through these power planes.
Okay.
I try and keep that all separate. The ground plane is more there as a like this one, the green one, is supposed to be to help with noise. So you have the singular ground plane that's sort of omnipresent throughout the board, and it's connected to ground by a ton of vias everywhere. And I think that helps with noise.
Right.
Yeah. That's a pretty hand-wavy answer, but that's the strategy that I'm going with.
I hear you.
Yeah, let's see what else can I say about that. The idea is you basically, with these higher current traces, is you need them to have as fat as possible and as short a path as possible. And same thing with the what's going on here with the actually, what if I do this? Let me switch. How do I switch my screen? Let's stop this for a second. And,
good. Okay.
There we go.
Yeah. There you go.
So this is a little easier to see what's going on, but this section here is that switch mode regulator, and it's fairly high frequency, right? Fairly high frequency and fairly high power. So that's kind of a recipe for noise. So the idea is that you want to keep everything as tight as possible, close together. And then, of course, the layout was generated mostly by WebBench.
Okay. So WebBench also tells you how to do the layout as long as along with the circuit, but also with the layout. Oh, very good. Oh, very good.
And like then reality sets in, and I don't have like this board that's just like they have, and I need to get things to certain places. So it's based on their design.
I see.
But yeah, this is the actual controller, and then these guys right here are the big power MOSFETs, and it's like input, ground, output.
Yeah, man, monster. And then down there by C13 is you got your big capacitor, 330 microfarad there. Is that the one?
Yes.
Yeah.
Yep, that's the one. And then big plane. So flip this over here.
Yes, look at that. There you go.
Yeah, right. It's got a bunch of bypass caps, these guys here. All that's like right close to the chip itself.
Yeah. Well, fantastic. So this is such a great platform to start working off. I mean, it's just beautiful, man. The work that you've done that has gone into this, huge kudos to you, man. Huge. Lots of respect.
Good. I appreciate it so much. Thank you. It's so fun to talk. It's great.
I've thoroughly enjoyed it. Any more information that you want to convey about the board, or future, like aspirations or anything something we haven't spoken about? Or?
Well, we need a lot of help with the firmware for this thing, right? So if anyone is interested in working on that, we have GitHub repository. There's discussion on there. You can hit me up on Twitter. We can get you on the Discord. But yeah, any kind of help there is good. Just kind of working on this thing nights and weekends, right? So I don't have like a ton of time. Definitely don't have as much time as I would like to put into it. So anyone that wants to help out in any way, it's totally appreciated. Or if you just want to fork it.
Oh yeah. What about helping financially? Is there some sort of like a place where people can send Bitcoin to you or anything like that?
Yeah. I should put maybe an address on the GitHub repo.
Good.
I mean, that would be great. I think at this point I probably need more time than
that's the engineers to problem. You've got enough money but the fucking time, bro.
yeah and I mean this is a cool project, right? So if there's someone working on a commercial project, or maybe even better, a commercial open source project that wanted to like have me work on this for them, that would be really cool, right? That could really accelerate this design. Is someone who wants to pay to like get this done, whether that be for another product of their own or
okay. Would this be through your company, or would it be individually?
We could do whatever makes sense, right? Like I work full-time for my company.
Is it your company that you own 100%, or I mean partners with?
I'm a co-founder. Yeah.
Okay.
My company is Geoscene, and we're an IoT engineering consultancy. So we do a lot of like IoT integration work. And I spend most of my time doing work for them. So, depending on what someone wants to do, we could set a contract through Geoscene to make some Bitcoin hardware. We'd love to do that. That's probably the best way to get a bunch of work done in a hurry. We're very well set up to do contracting at Geoscene.
Okay.
But I'm open to other situations too. So I would love to work on this full time. So maybe we could figure something out. If someone has some ideas.
Yeah. say, for example, if I were to fork the project, obviously I would give credit to upstream, and I'd need to rename it. Maybe, I don't know, Bitmace or something like that. Who knows? But that sort of stuff is also, that sort of stuff, you're okay with that sort of stuff too, right?
Yeah. No, I picked an open source license. It's MIT licensed, and
I noticed
I
that.
like consciously did that for a reason. So I am cool with it. I think sometimes people pick that and maybe someone forks it and they're not actually cool with it. But
yeah. Oh well, stuff them.
For the time being, I'm very cool with it. So please do it. Call it, Skot sucks or Bitaxe is the worst or whatever. I don't know. Just make something cool, right? And open source it, right? Like that, that is what we need to do to like move this forward, right? And I've definitely had some people working on this who have forked the project and are kind of working on their own thing, and they're like, oh, I don't want to, I'm like, well, post your GitHub. Let's do this, let's see what you're working on. And they're like, oh, well, it's not finished, I need to put on the finishing touches. And it's like, don't worry about that. Post it. We'll be nice. We just want to see what you're working on. And then you'll be surprised about the number of people that kind of come out of the woodwork to help you. So
yeah. Well, I'm super impressed with this. So how do people get hold of you? What's your contact information?
Let's see. I'm Skot, Skot, on GitHub. So you can just get me at Skot. I'm Skot, Skot 9000 at Twitter. So you can message me on there. I don't know. How do people like to get in touch? That's probably the best way, right?
Yeah, Twitter's good enough. It's all good. Yeah. It's all good. Well, yeah, Skot, right? Man, I appreciate your time. Thank you so much for coming on board and explaining this project to us. Absolutely wonderful.
Thank you. This has been great. Thanks for the opportunity to talk about this stuff. And
cool.
I like to hear about your project too, and I think you got something good on your hands here.
Brilliant, mate. I'll keep you posted about that, and also maybe the contracting thing. I might need some work done.
Okay. Yeah.
Okay. Let's end it right here.